Hello everyone, welcome back to Delkin Cards. In this video, we will finally be taking a look at the monstrous problem 3, which is the hardest problem on day 1. We have a long road ahead of us, so without further ado, let us take a look at the question. So this is a combinatorics question. The problem statement is as follows. Let a1, a2, a3, be an infinite sequence of positive integers, and let capital N be a positive integer. Suppose that for each n greater than capital N, an is equal to the number of times an-1 appears in the list a1 to an-1. Prove that eventually at least one of the sequence, the odd terms or the even index terms, is eventually periodic. Okay, so this is quite a tough problem given that it's combinatorics and it's the hardest problem on day 1. So before going into the solution, I do want to make a couple of caveats. So disclaimer, firstly, there are quite a number of solutions going around which seem to be merely sketches of the eventual solution. And with all due respect, the hardest part of the solution is actually checking through the details. So be very careful of solutions which outlines the general approaches and then claim that, oh, this is an obvious problem. So the problem is actually not as easy as it looks. Filling in the blanks is the hard part of this problem. So what we are going to do is we'll go through the problem as detailed as I think is necessary to be convinced that all the blanks have been filled. Some of the details will be not written on the slide, but it will be covered by what I'm about to say. So do listen to the audio. And of course, be prepared for the ride because it's not going to be a short solution. Okay, so before going into the solution content in detail, let us start by trying to understand the problem statement a little bit better. And to do this, we are going to use a histogram to try and visualize what is happening as we construct the sequence. So suppose that for the purpose of illustration, capital N is 6 and this is the starting sequence. So over here I have my histogram. So for the number 1, I already have 2 blocks. And the number 3, I already have 3 blocks. And the number 2, I have a single block. So the vertical height of the number is the count of the number that has appeared so far. So, and in red is the last term that has been added. So 3 has been added to this column. And so what we do from now on, after n greater than capital N, we are supposed to look at the number of times the last term has appeared so far. So in this case, this is given by the height of that column. So I added 3 as my last number. The height is 3 because 3 has appeared 3 times so far. So the next term will be also added to column 3. Okay, maybe that was a bit confusing because the number 3 repeats both as the height and the entry itself. Now, maybe this is a little clearer. Now the last term is 3 and it is at height 4 because it has appeared 4 times in the sequence so far. So I look at the height. This is the next column that I'll be adding it to because the next term in the sequence is 4. So I'm adding a block to column 4 and this is adding a block at height 1, and indeed 4 has only appeared once so far in the sequence. That's why the new block is at height 1. So I'm going to look at the height, and now I'm going to add a block to column 1 because the next term in the sequence is 1, and so on and so forth. Now the height is 3. I'm going to add a block to column 3. The height is 5. I'm going to add a block to column 5, and so on and so forth. So hopefully this illustration is clear to you what we are doing. Do make sure you understand what we are doing here with this histogram because this is going to be one of the key instruments that we are going to use in our argument. So make sure you understand why we are adding blocks to which column and so on. Okay, the first observation that we can make is that the sequence an is going to be unbounded. And this is quite easy to see. If we assume on the contrary that an is bounded by some number let's say call it M, then what we are saying is there will be no blocks that is going to be beyond column M. And not only that, you cannot have any column that will have height above M, because once it goes above M, then that height value will force a block to be added next to that column that is above M. So it means our entire histogram is confined to the M by M box, which has only finitely many spaces. So that is a contradiction to the fact that the sequence will be infinitely long. So indeed, AN is unbounded. Okay, the next observation is that starting from position n greater than or equal to capital N, the pairs of consecutive terms an plus 1 are never going to repeat itself. And this is again quite clear from the diagram, because by the way we are constructing the diagram, an plus 1 is the xy coordinate of the nth block. So for example, over here, this block that I just added, well, it is there because I'm adding 1 to the sequence, and the next term is going to be the height 3. So 1, 3 is indeed the xy coordinate of the block over here. So because the blocks are all going to be in unique position, these pairs are never going to repeat themselves. Okay, I'm now going to define a term that is going to be useful for notation purposes. So I'm going to call h subscript t of I to be the height of column I at time t. Okay, so time t refers to after I have exactly t terms in my sequence. It's easier to use the notation t than small n to help us intuitively understand what is how to think about the sequence in terms of step by step. Okay, so right now we have the basic setup. We'll break up the problem into two main parts. So the first part of the problem is to try and understand the behavior of h. So to do this, one thing that you might notice after a while, after experimenting a bit, is that the columns are going to have non-decreasing height. So let us prove that. But before proving that, we need to make a small definition, because I have to deal with this annoying initial configuration, which might, obviously you can tell from this diagram, the columns are not of decreasing height. And that's because the initial first capital N terms, I mean, there's no control over it. So I'm going to have to limit my claim of the non-increasing height to sufficiently large columns. So to do this, I'm going to have to define a constant m. I'm going to define this to be the max of the first n terms as well as the number n itself plus 1. So this m is going to be larger than any of the first n terms as well as the number of time steps taken before I have control over my sequence. And as I tried to explain in words just now, what we are going to prove, claim 1, is that at all time, whenever we are looking at columns that are at least column m, then the columns have non-increasing height. So if j is bigger than I, then j have a less than or equal to height than the height of column I. Okay, to prove this, it suffices to look at the case j equals to I plus 1, because then I can just iteratively repeat the claim until I get to the desired j. So let's reduce the case where j equals I plus 1. Okay, now follow the argument closely, because there's a bit of logic that needs to be followed. So over here, I have an appearance of I plus 1 in the sequence. Now, what I'm going to do is I'm going to map each appearance of I plus 1 injectively to an appearance of I in the sequence. So if I can do that, then obviously the number of appearances of I plus 1 is less than or equal to the number of appearances of I. So if I plus 1 appears in the sequence, how did it end up there? Well, firstly, I plus 1 is bigger than m. bigger than, okay, actually it's bigger than m, which is bigger than a1 to an. So I plus 1 is actually not there because it's the initial part of the sequence. So it must be there because some block was added at height I plus 1. And because it is that height value, so that causes the I plus 1 to appear next in the sequence. But in order for a block to be stacked onto a column and be at height I plus 1, there must have been a block beneath it at height I. And because I is bigger than or equal to n, which is bigger than n, it means that this block must be added only after time n, right? Because in the first n steps, the best you can do is go up to height n only. So in order to get height I, it must have been a step that is after time n. And because it's added after time n, the rule of the sequence have already kicked in. You need to look at the height, which is I, and that appears as the next element in the sequence. So this means that the yellow block must induce a I to be added next. So from here, we can see that each appearance of I plus 1 can indeed be injectively mapped to an appearance of I. And this is injective because each appearance is tied to a blue and a yellow that is the yellow that is right beneath it. Okay, so hopefully this, again, this part of the proof is clear. But even though it may seem a bit too much abstract argument to keep in mind, the most important takeaway now is that beyond point M, the heights are always non-increasing. Okay, now, besides being non-increasing, I claim that the heights are all bounded by a certain constant. Now, to prove this, I'm not going to need the diagram. I'm just going to use equation. It's much simpler for this one. So the second claim is, I'm going to claim that the height of M is actually strictly less than M at any point in time. And you can tell from here that because the heights are non-increasing, so all the other heights after that are also going to be strictly less than M. Okay, how do we prove this claim? We assume on the contrary that there is some instant in time called T star where M has appeared in the sequence for the mth time. So this is the exact moment where the mth appearance of M appears. Okay, again, because M is strictly bigger than A1 to AN, all the appearances of M must happen after time capital N. Let us look at the terms before each appearance of M. Firstly, none of them must be M because you cannot have the appearance M yet because this is the mth appearance of M. So the M actually appears here, M then M. So before this M it cannot be M, before this M cannot be M because if we have M, it means the front M is the mth appearance of M. You see what I'm trying to say? So this cannot happen. So this means all the terms before that, even in the worst case scenario where we try to minimize the terms, we can only run through 1, 2, 3 until M minus 1. So no matter what, there must be some term before M that is strictly bigger than M. You see what I'm trying to say? Yeah, if you can only use 1, 2, 3 until M minus 1. You cannot use M. So no matter how you do it, there must be something bigger than M that appears before M. But the appearance of Km, by definition of the sequence rule, this means that K has appeared M times. So the K column is already at height M at that time. And K is bigger than M, so it's on the right side of the diagram that we saw just now. So K is bigger than M, but it is already at height M, whereas M at that point in time is still at height less than M. So this means that we contradict claim 1 because we have a larger number but the height is strictly larger. So this proves claim 2. So again, there's a bit of logical tussling that you need to do. So with each of these claims, do feel free to review it if it seems a bit fuzzy. But once again, once you're convinced, the main takeaway for this is the height of all the right side columns is bounded by a constant, which is capital M. So what can we then say about the behavior of all these heights? Okay, this is actually quite an interesting slide, so pay attention to this. So at time 0, we saw that the height is going to be non-increasing. At time 1, the height is not increasing. At time 2, the height is not increasing. Everything here is bounded above by capital M. Now, I want you to follow the behavior when we look vertically. So as time increase, obviously the heights are only going to be non-decreasing, right? Yeah, only adding blocks over time. So this is a sequence that is non-decreasing and is bounded above by M. So it must converge to something. Let's call the height as the eventual height to be H underscore M. Same thing, if you look at the M+1 column, as time passes, it is having non-decreasing height, but it's all bounded above by capital M. So again, it must converge to something. Call it H underscore M+1. Same for column M+2 and so on. And because of this non-increasing behavior row-wise, each of these limit is also going to be non-increasing. So because they are all bounded below by 0, this non-decreasing sequence must eventually converge to a constant C. Okay? Now, in fact, even though it's bounded below by 0, I can conclude that C is greater than or equal to 1 from the fact that the sequence is unbounded. Because the sequence is unbounded, there will be blocks that keep appearing in new columns. So it cannot be the case that eventually the columns stop having blocks being added to them completely all the way to the right of something. So even if I don't know that every column have a block, but I know that it cannot be the case that every column has 0 blocks. So C is going to be greater than or equal to 1. Now comes the most important claim, which is that the numbers 1 to C are actually the ones that will appear infinitely often in the sequence. And all the other numbers, C plus 1 onwards, they only appear finitely many times in the sequence. How do we prove this? Okay, firstly, there exists a big enough number L such that all the heights at time infinity is equal to C. So this is because the limits just now we saw, right? Eventually the height will converge to C. So at some point it's going to be C forever. Now I'm also going to just choose L to be bigger than M to be safe, so I can don't have to worry too much of all the initial configuration effects later on. Now this means that the numbers 1 to C are going to appear infinitely often. Why is this the case? Well, for each of these columns, when the block is added to that column, its height is going to cause that number to appear. So the first time we add the column L, 1 is going to appear again. Second time we add the column L, 2 is going to appear again. So this column will cause the number 1 to C to appear once. Same thing for this column and so on and so forth. So all of this column will cause all these numbers to appear at least exactly once per column. So it appears infinitely often. On the other hand, if we look at any other number j that is bigger than C, we can very safely say that it will not appear more than L times. In fact, if it appears at least L times, then each time it gets added to height L, firstly 1 to C will appear, will have height L at some point in time. So it will contribute blocks to the L column. But if J also have at least L appearance, then at some point the J column will have height L. So once again, you'll contribute a block to the L column. This will contradict the fact that HL is equal to C and not larger than C. Okay, so these two together prove the claim. Why is this useful? This is actually very important because this basically tells us this very important picture that will conclude the first half of this proof. Namely that beyond some point, beyond some column L onwards, the columns are all going to have height that is capped by C. In fact, we saw that in the proof earlier that not just capped by C, it's going to be exactly C because the eventual height is the limit, right? So the limit H, remember the H, capital H underscore the index, all those limits are eventually C by definition from the point L onwards. So this will all eventually become height C. At the same time, only the columns 1 to C can appear infinitely many often times. And we saw in the proof earlier that if we are looking at columns larger than C, they cannot appear at least L times. So this means the blocks are all going to be constrained to this part, and this part. And this means that beyond a certain time capital T, we are only going to be adding blocks to the two blue regions. So either here or here, because here will eventually run out of space. So after some very long time, blocks are only added here or here. And in fact, they must alternate between the two regions. Because if you add here, the height is a large number, which will then cause us to add a column to this part here. And this part here, the height is of a small number, so the next block will be added to this part here, and so on. So you alternate between a small column and a large column. Here, 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 and so on. What we are going to try and prove is that the small column subsequence, because it's alternating, right? The small column subsequence is basically, it's going to be like the tail of either this or this because of the alternating behavior. Yeah, so the small number subsequence, we are going to prove that is eventually periodic. So now that we have obtained this picture, we can try and move on to the second part of the proof. And to do this, we are going to take a closer look at the behavior of the situation from this point onwards when we are alternating between small and large. Okay, so suppose now that we are at a particular point in time where we have just added a large number and we are going to add a small number next, but we haven't added that small number yet. Okay, the first thing I want to point out is that if we have the configuration of the blocks here, we can actually derive the configuration of the blocks here. How do we do that? Well, you might have noticed the pattern by looking at this specific example that I have on the slide now. If you have 6, 4, 4, 3, 2 as the heights of all these columns arranged in descending order, you notice that the row lengths here are 6, 4, 4, 3, 2. Okay, so I've described the pattern on how to derive this, but why is that true? It's also quite simple to convince yourself of this. If you look at the number L, for example, height L, for example, there are already 5 blocks being placed here. And each time the block is placed in height L, it must contribute a block to column L next. The same thing, let's skip all the way to height L plus 2 to make this clear. If I look at height L plus 2, there are already 4 blocks placed here. Each time they are placed here, it must have contributed a block to column L plus 2. Same thing, the height here whatever this height is, it must have contributed exactly 1 block to this column. So this pattern over here is basically the transpose of this, but you need to arrange it in increasing row length. So this is quite useful to point out to help you understand how are we adding, how can we derive this pattern from the pattern here. Okay, but that's not the most important thing that I actually want to point out on this slide. The most important thing I want to point out is, how do you predict how the rest of the sequence is going to evolve just from knowing the configuration here, as well as what column are you adding to next. So these two combination of information is going to be enough to specify the rest of the sequence. Let me explain. Suppose you are now adding to the kth tallest column. So remember, knowing which column you are going to add to is part of the information I need to specify to you. So if you know that you are adding to the kth tallest column, then what is going to happen is that, let's say for concrete illustration purposes, I'm adding to the second tallest column. So either here or here will have been the second tallest. But if I add to the second tallest column, then that will be the second time this particular height appears, which means that I'll be adding to the second row next. You see what I'm saying? Let's take another example. Let's say after this is the fourth highest column now. First, second, so fourth. So if I'm adding to the fourth tallest column, this height would just appear for the fourth time. So following that, the block I'm adding is going to be to the fourth row. You see the pattern and why it's true? So this is quite important, because now what happens next? After I add to the kth row, well, the kth row by definition is the height of the tower that I just added to. So I'm going to, after this, add the block to the kth column. So be very careful here. This is the ranking in terms of the height. The k here, you look at the rank first, is the kth tallest column. So you go to the kth row, and then now you go to the column of index k. Okay, so now you can repeat this whole thing over and over again. I'm adding to the column of index k, but to determine what happens next, I'm going to look at the rank of its height. Let's say it's the 11th tallest. So if it's the 11th tallest, it means after this, I'm going to add to the 11th row, and then the 11th column, meaning the column of index L, etc., etc. So I look at the rank of its height. Let's say it's the ith tallest. Then I add to the ith row and the ith column, and then I look at the index of the height. Maybe it's the jth tallest now. Then I add to the jth row and then the jth column, and so on and so on and so forth. So I'm going to call what I just described, the key behavior property. Okay, it's for reference in the subsequent slide. So what I just described is called the key behavior property. It's just a very poorly construed term, but hopefully this key behavior property is clear, because we are going to use this heavily in the rest of the proof. And how are we going to use this? Well, two ways. The first is I'm going to prove our last claim that we need before we finish off the problem. I'm going to prove that there exists capital D such that the height of I minus height of j absolute value is bounded by D for all ij between 1 and c and all t bigger than capital T. What this means in words is that at any snapshot in time, of course after capital T, if I look at any two columns, the difference in their height cannot be arbitrarily large. It must be uniformly bounded by a certain constant d. Now, I'm in fact going to prove just the case where j equals I plus 1. And then you can get the general case, general version by applying triangle inequality and chaining it together. And then you can just increase the constant to take care of the triangle inequality. Okay, so how do we prove this? The proof of this for one direction is quite straightforward. We first prove the case where we want to show that the height on the left, on a more left index, cannot be too small relative to the height of something of a more right index. Okay, so this direction is quite easy to prove because if we look at any appearance of xi plus 1, where x is bigger than or equal to L, the fact that x has appeared I plus 1 times means that before that, x must have appeared I times. So xi will appear somewhere before that. So each appearance of I plus 1 can be mapped to an appearance of I in an injective manner. So we've seen this argument before. So this means that the appearance of I cannot be too little relative to the appearance of I plus 1. But you may protest that I've assumed x is bigger than or equal to L for simplicity because I don't want to deal with all the initial configuration business. But you can very easily take care of that by just throwing in a gigantic constant. Like if you assume in the worst case that all the terms before capital T is all I plus 1, then even in that worst case scenario, we are not going to be too worried because you can just throw in this constant to take care of that. Okay, so hopefully this direction is clear. I'm not going to belabor on that. I'm going to spend more time proving the other direction, which is interesting. So we want to show that this difference here is bounded by some constant. We assume on the contrary that, well, this difference, something on the left, can be way, way, way bigger than something on the right. So what is the problem here if we assume this? Okay, so I'm going to use my picture to help explain things. So we assume on the contrary that this is I plus 1, and I can make this gap gigantic, as large as I want. Now, by the direction of inequality we have already proven, note that 1, 2 until I minus 1, they are all towers to the left of I. And we've shown already that something to the left cannot be too small relative to the towers on its right. So, and we can chain that inequality together using triangle inequality. So there is some super big constant you can throw in here where all this height cannot be too small relative to the height of I. Same thing by flipping the argument around. All these are to the right of I plus 1. So all these towers again cannot be too tall relative to the height of I plus 1, which is on their left. So if I can make this gap super, super big, I can make it so big that even if in the worst case scenario, all these towers here, even in the worst case scenario, they cannot be too short relative to this. So by making this super, super, super way taller than this, right? All these can be made taller than anything on the right half here. You see what I'm saying? All these are capped in height relative to this. All these are capped from the below relative to this. If I make this gap arbitrarily large, eventually all the heights are bigger than all these heights. So let's see why is that a problem. Let's say there's a point in time where I just added a block to the ith column and the gap is so big that what I just described is true. Then adding to the ith column we now reference the key behavior property that I described earlier. The ith column, in terms of its ranking of height, it must be among the first I tallest columns, because the first I tallest columns are all on this side. This means I'll be adding to one of the first I rows next, which means after that I'll be adding to one of the first I columns. And once again, the first I column dominate the ranking in terms of height. So I'm again adding to one of the first I in terms of rank, which will then add to the one of the first I rows, and so on and so forth, which means we are never ever going to touch columns I plus 1 to C again, which is a contradiction. Quite a neat little argument, and it might take a while for you to wrap your head around. So do feel free to pause and review this argument again if you need to. But this concludes the proof of claim number 4. So we've proven claim number 4, and we are now on our way to finally finishing the proof. How do we do this? I'm going to involve two pieces of information here. First is what I call frontier shape. So if I look at this, the frontier shape, very loosely defined, is just basically the outline, the upper outline that I'm drawing. So like something, then go up by 1 step, 2 step, -4 step, plus 2 step, and so on. So you know what I mean. So this is like the frontier shape. And I'm going to also combine that piece of information with which column am I adding to next. So let's say I'm at a point in time where I'm going to add a small number next, not a large number. So I'm going to have the frontier shape as well as what column I'm adding next. From this, we know the behavior of the sequence thereafter in terms of the small numbers that we'll be adding forever and ever. Why? Recall the key behavior property slide. By the key behavior property, I know which column I'm adding to. From the frontier shape, I can tell what is its ranking. So I know what row I'm adding to next, and so I know what is the next small number column I'm adding to next. And I know what is the updated frontier shape. Again, I can get the rank. And so after that, I know what is the next small number column that I'm adding to next again. I know what is the updated frontier shape, and so on and so forth. So if I just focus on the small numbers that I'm adding from that point onwards, it is fully determined by these two pieces of information. You see that? So the final move is to realize that by claim 4, there's only a finitely many possible frontier shapes that can happen. And obviously, the number of small number columns is only 1 to C, so again, finitely many options. So this combination of information is there's only finitely many options, and therefore it must eventually repeat. And because this combination determines the rest of the sequence, this tells us that we will be in a situation where we get periodic appearance. Why is it periodic? Well, the first time this combination appears, let's say there's a certain combination that repeats, and we found repetition 1, repetition 2. Okay, first time repetition 1 appears, we already know that it determines the rest of the sequence, so you continue, and then it hits repetition 2. When repetition 2 happens, we are back in the exact same scenario, so it must be the case that the subsequent small number terms is the same as what happened when we left off from repetition 1. So we'll continue, and then it will hit the repetition again. And then the terms after that, again, is the exact same when we left off from the repetition. So this means that the small number terms are going to be periodic. And of course, the small numbers alternate with the large numbers, so it's going to be one of the tails of these two sequences. Yeah, so this has been quite a ride, and I hope you are able to understand all parts of this proof pretty convincingly. So do stay tuned to the channel for more videos where I'll be covering the problems from day 2 of the IMO. I hope you enjoyed the problem. Let me know what you think in the comment section and see you soon.